Hello everyone, I'm Norman Wahlberger and welcome to Algebraic Calculus. In today's video we're going to look at Gregory-Newton interpolation, which is perhaps the central result in the difference calculus. It's a core theorem or formula and it's really full of applications and interest. So to motivate our story, let's consider this sequence. It's a 5 sequence. 2, 0, 4, 20, 54 associated to the numbers 0, 1, 2, 3, 4, and its name is S. So two natural questions that we might be interested in is how can we continue or extrapolate this sequence? For example, if we were interested in the value at 5 or at 6, how could we possibly do that? We've already seen an answer to that. We know that the difference table that we can create will help us do that. A second related question is how to find intermediate values, or in other words, interpolate between the data points that we already have. This is a different question. This is a more subtle question. For example, suppose we were interested in the sequences value at 2.5, or 1 9/10, or some other intermediate value. Okay, so people who were interested in this kind of question in the 17th century included John Wallis, who was interested, for example, in the question of how to define powers of x, where the power is not necessarily an integer power, but a rational number. How do you go about dealing with that kind of function? And then James Gregory and Isaac Newton are the stars for today. James Gregory is a very brilliant Scottish mathematician whose life, unfortunately, was very short. But he did discover a lot of formulas that are nowadays attributed to Leibniz and Newton. And probably if he had lived longer, he would have been a major contributor and a sort of a star of calculus. But in any case, today we're going to look at a formula called an interpolation formula that they discovered. This problem has a direct geometrical content. We can think about the sequence 2, 0, 4, 20, 54 as points in the plane associated over the numbers 0, 1, 2, 3, 4. So there's 2, 0, 4, 20, 54 in this scale that I've set up here. And one way of saying what we're trying to do is we're trying to find a function, a continuous function, preferably a simple one like a polynomial function, that would be the best, through these finite set of data points. So we'd like to continuously join the points. We can always, of course, make a spline, but we want to do it nice and smoothly so that we can extend the curve and also so we can read off intermediate values. So in some sense, what we're interested in is going from something discrete here to something which is analog. Discrete data points, in this case 5 points, and we want a continuous, smooth extrapolation or interpolation of that. And also what we're interested in is to be able to do this in a robust way. What do I mean by that? It means that suppose that we have drawn or calculated a curve that goes through these 5 points, and then someone comes up with a 6th point that's in this sequence. We have some new data. Maybe the new data point is 78. Okay, so now there's a new data point. That means we most likely have to adjust the calculation that we've just obtained. And we'd like to do that in a minimal kind of way. So instead of having to redo the entire calculation, we'd like to use what we've just calculated and modify it in some fashion to get the polynomial function for the 6 points. That's what I mean by being able to do this robustly. Now there's a very natural algebraic approach to this, which is actually quite important. So we're trying to find a polynomial, let's say p of n, that agrees with our sequence for values n equals 0 up to 4. And thinking about it a little bit, we recognize that probably what we need to do is look at a polynomial of degree 4. Say a0 plus a1n plus a2n squared plus a3n cubed plus a4n to the 4th. Because there's 5 data points that were given, 5 pieces of information, and so here there are 5 unknowns. So that sort of works out. We expect that we might have a good chance of being able to find such a polynomial. And how do we go about doing it? Well, it's pretty obvious. We're going to take this formula and consecutively introduce n equals 0, 1, 2, 3, and 4. And what we get is then evaluated to the various sequence values. So when n is 0, then the polynomial simplifies and we're just left with the first term. That's an important observation. Okay? You have a polynomial, you plug in 0, you get just the first term, the constant term. And that's supposed to be 2. Okay, then when you plug in 1, well, you're going to get the sum of the coefficients. That should be the second term in the sequence, which is 0. You plug in 2, you're going to get 2 here, and a 2 squared, and a 2 cubed, and a 2 to the 4th. So you're going to end up with this equation equals 4. And then here's the corresponding thing for 3 and for 4. So you have then 5 linear equations in 5 unknowns. That's a happy situation. That linear algebra is all set up to solve for us. So we can do it by hand, but we can also get a computer very quickly to tell us what the answer is. And it turns out then that we can evaluate these 5 numbers, and it turns out that the polynomial is, in polynumber language, 2 minus 3 alpha plus alpha cubed. Now I might mention that when you're setting up this system here, if you use linear algebra matrix formulation, there'll be a matrix of coefficients that's involved, and that will be a very special matrix called a Vandermonde matrix. It basically has rows which are geometric series, 1, 3, 9, 27, 81, and so on. So we're touching base here with an important chapter in matrix theory. But in the difference calculus, we take a very different point of view to how to solve this problem. And center stage are the very special sequences that we found in Harriot's triangular summation table. I remind you that looks like this. It's otherwise like a Pascal array with the rows of the Pascal triangle successively down. And it's really the columns that we're interested in. And these columns we call them H0, H1, H2, H3, H4, and so on. And they are really the important basis elements. They're really sort of the fundamental building blocks of sequences from the difference calculus point of view. Okay, in terms of what they are explicitly, here are the representations in terms of our rather special notation for on sequences. H0 is a constant. There's a 1 there. There's a square bracket and a pointed bracket. H1 is just n. Remember, we like to use n to denote the polynomial value that's generating the sequence. The indices here are corresponding to n on this side, and over on this side corresponding to k. And over here is the next one is the sequence n choose 2, and then n choose 3, n choose 4, and so on. So this entry here will be 0 choose 4, 1 choose 4, 2 choose 4, 3 choose 4, and then 4 choose 4, 5 choose 4, 6 choose 4, and so on. This matrix is really a two-dimensional analog of an on sequence. It extends in this direction, it extends in this direction. And so we might, well, introduce some kind of on sequence notation for it. And I suggest that we use this, that h is equal to, this is double bracket on this side, double pointed bracket on the other side, and inside the element of the n-kth object, the thing in the nth row and the kth column, which is, very simply, n choose k. So with respect to the standard indexing of an array, n on this side, k on this side, but crucially both starting from 0, then the n-kth element is n choose k. And we could call this an on matrix because we can extend it. This is just a partial picture. This is just a clip of this on matrix. And in that regard, the columns of this thing here that we see are also clips. Remember, there was a distinction between the sequence, which lays out entirely the elements in terms of an expression like this. This is actually the official sequence. This is a clip of that sequence. It's a partial snapshot which shows you part of the information, but the 3 dots telling you that there's more information that you're not seeing. Okay, so these particular sequences play a crucial role in the difference calculus, and especially in these questions that we're interested in terms of interpolation and extrapolation, and crucially the Gregory-Newton interpolation formula. All right, so let me explain why these sequences H0, H1, H2, etc. are so important. So here is a smaller copy of that matrix H that we've just been looking at, and I want to explain to you how we can take linear combinations of sequences. So sequences are quite general objects. They're a lot like vectors, sort of vectors that keep on going. And just like vectors, we can add them and take linear combinations. So let me illustrate that with an example. I hope it'll be clear. So let's look at the linear combination 2h0, 2 times h0, minus h2 plus h3. Okay, that's a linear combination of sequences. I claim that's also going to be a sequence. Let's look at it from the point of view of what it looks like in terms of a clip. So we're going to take 2 times this one and subtract this one and add this one. So if we do it sort of element by element, the first one will be 1 times 2, that's a 2, minus 0 plus 0, so that'll be 2. And then the next row, it'll be 2 minus 0 plus 0, that's 2. And the next one, 2 minus 1 plus 0, that's 1. Then 2 minus 3 plus 1, that's 0 again. And then 2 minus 6 plus 4, that's another 0. So we had 2 here, 1 here, 0 here, 0 here, and over here. 2 times this, minus this, plus this, that'll be 2 again. So that's a clip of this linear combination sequence. And officially what that is in terms of our official way of representing a polynomial or polynumber on sequence, is we just take the corresponding combination of these various hi's. So here's h0, it's the polynumber entry 1. Here's h2, n choose 2, and here's h3, n choose 3. And more explicitly, if we put everything inside, we get 2 minus the n choose 2 is n times n minus 1 over 2, and the n choose 3 is n times n minus 1 times n minus 2 over 6. So we have to take that sum, that combination of polynomials, or actually binomial coefficients. And when we do that and work out the algebra, we get 2 plus 5/6 n minus n squared plus 1/6 n cubed. So this is actually the official name for this sequence S, this linear combination, and here's a clip for it. Now I want to illustrate why this kind of representation is useful for us by looking at this sequence as if we were just presented with it for the first time and we were trying to analyze it using a difference table. Okay, so here we've got the same sequence, 2, 1, no, starting here, 2, 2, 1, 0, 0, 2, and it carries on. And actually the next one is 7, so we've included that one as well. Okay, so let's take that and take a difference of it. So we're going to create a difference table. There's delta of s, then delta squared of s, delta cubed of s, delta to the fourth of s. So the differences here are 2 minus 2 is 0, 1 minus 2 is minus 1, 0 minus 1 is minus 1, 0 minus 0 is 0, 2 minus 0 is 2, and 7 minus 2 is 5. And then the differences of this one are minus 1 minus 0 is minus 1, 0, the difference here is 1, difference here is 2, the difference here is 3, and the next one, the difference here is 1, 1, 1, 1. The pattern's clear at that point, and then the next differences are all 0. And all subsequent differences are also 0. So I want to especially draw your attention to the top row of this difference table. All right, that turns out to be crucially important. The top row of this difference table. So we started with the actual sequence in the first column, or the 0th column officially. And now we're looking at the first row, or the 0th row. Its entries are 2, 0, minus 1, 1, 0. And I want to just point out that these numbers are directly related to the expansion of this S in terms of these Harriot sort of basis binomial sequences. Notice we have 2h0 minus h2 plus h3. And notice along the top row here, we have a 2 in the 0 spot, a -1 in the 2 spot, and a +1 in the 3 spot. So if we knew this beforehand, we could have predicted what the first row would be just by looking at the expression of the sequence. And conversely, if we didn't know the sequence, we could obtain the sequence by reading off this first row and just creating the corresponding linear combination of the Harriot sequences. This is very important. And let me explain why that is. So it has to do with the fact that taking differences are so easy in the Harriot basis, because the Harriot basis is created by each one is the sum of the previous one. And that means if we go left, we're taking differences. So the difference of this one is this one. The difference of this one is this one. The difference of this one is this one. And we can encode that here. The difference of h sub k plus 1 is h sub k. So if we apply the difference to this linear combination, what's going to happen? Well, what's the difference of h0? So the difference of h0 is what's to the left, but there's nothing here. Right? All these differences are 0. It's like when you go to the left, h0 falls off and is killed. There's nothing left there. So the difference of this thing is 0, vanished. The difference of h2 is h1, so this becomes minus h1. And the difference of h3 is h2. So we just push all the indices over 1. We lower all the indices. And again, if we want to perform another difference, which is going from this one to this one, then what we're doing is we're, again, just shifting everything over. We get minus h0 plus h1. We shift over once more, the minus h0 gets killed, and we just have an h0. And then we do it once more, and the h0 is killed as well and gets 0, and then from then on it's always 0. Now, so the sequence delta S is minus h1 plus h2. And there it is there. And the top entry here, the top entry is, well, the top entry of all of these ones, have a look here, right? The top entry of all these h's, they're always 0. The top entry is always 0, except for the sole exception of h0, whose top entry is 1. So if you have a linear combination of h's and you want to know what's the top entry, you can ignore everything except the h0. It'll just be the coefficient of h0. So we can immediately see here that the top entry is going to be 0 because there's no h0. And we can immediately see here that the top entry is going to be minus 1. And we can see immediately that the top entry here is positive 1. And the top entry here is 0. That's the reason why the coefficients of the sequence expressed in this Harriot basis ends up coinciding with exactly these numbers that appear in the top row of the difference table when you start with the sequence on your left. So here's our Gregory Newton interpolation formula, which basically codifies what I've just said. Generalize it to the general situation. So for a polynumber on sequence S of degree k, so this is an on sequence which is given by a polynumber or a polynomial, and we're told that that polynomial has degree k. Okay, so that sequence then can be written as a linear combination of the Harriot sequences, the hj. The sum going from j equals 0 to k. So it's a linear combination of h0, h1 up to hk. And this tells you what the coefficient of each of those hj's are. Each coefficient is the result of doing a difference to the original sequence j times. The jth one is you take the difference j times, and then you evaluate it at 0, which means look at the top entry of that corresponding column in the difference table. So these are all differences. That means they're the things that populate the difference table, and these are just the top entries of those, exactly the same thing that we were talking about in the previous example. Now, if we want to make the dependence on n more explicit, if we want to know what's the nth term of the sequence, Well, then Sn is going to be the sum, j equals 0 to k, of still delta to the j of s at 0. And now hj of n is the binomial coefficient n choose j. That's the value of h sub j at n. It's like we're going over to the jth column and going down to the nth row of the Harriot matrix H. Okay, the proof, what's the proof? Well, we're assuming that S is a polynumber or polynomial of degree k. Now, a polynumber of degree k can be expressed in terms of the hj's, because the hj's form a basis for the space of polynomials. h0 is of degree 1, h2 is of degree 2, h3 is of degree 3, etc., up to hk is of degree k. So whenever you have a situation where you have polynomials that have that property, that their degrees are marching up one by one, then they automatically form a basis of the space of degree k polynomials. All right, so that's just a little basic exercise in linear algebra. So we know that S can be written as some linear combination of bj, hj. Hj's are the sequences, and bj's now are just numbers. They're rational numbers. Maybe I should say that. Okay, so for some bj, which are rational numbers. And we'd like to show that these bj's are actually these things. So how do we do that? Well, we apply the difference operator delta to both sides. The nice thing is we know exactly how the difference operator acts on hj. The difference operator is linear. That's maybe also something that we need to say. The difference of a sum like this, it's a linear combination of all the individual ingredients. So we know that when we apply delta to hj, we're just getting the previous hj minus 1. So if we apply delta j times to s, what's going to happen is that as we shift over, every time we get to 0, then it falls off. The first thing is going to be b sub j times this hj that was here is getting shoved over j times, and so now it's h0. And then all the previous terms have been killed, and all the other terms are then just the subsequent ones. There's bj plus 1 times h1, all the way up to bk times h to the k minus j. Okay, and now when we look at this difference sequence evaluated at 0, that's the top entry, the only thing that contributes in this combination is the h0, because as we've said, the top entry of h1, h2, and all the other ones are all 0. So the only entry that contributes is bj, and we get immediately bj. So this is sort of a restatement of the argument that I showed you in the special case on the previous slide. So that identifies that, yes, this coefficient has to be the jth difference of s evaluated at 0, and that establishes the Newton-Gregory or Gregory-Newton interpolation formula. Okay, and it's a key formula in the difference calculus. So let's illustrate the power of this formula by applying it to the original problem that we started the lecture with, which is to understand this sequence in a better way by getting a polynomial function through the finite set of data points. The sequence was 2, 0, 4, 20, 54, associated to the chain 0 to 4. So what we're going to do is we write down the sequence 2, 0, 4, 20, 54 in a column. We like to put our sequences in columns because then we could use an Excel spreadsheet or any kind of spreadsheet, and we could generate these differences very succinctly and easily. So here's the difference table. 0 minus 2 is minus 2, 4 minus 0 is 4, 20 minus 4 is 16, 54 minus 20 is 34. The differences here are 6, 12, and 18. The differences here are 6 and 6. The difference here is 0. So this then is that top row of the difference table. We get a 2, a minus 2, a 6, and a 0. Okay, so according to the Gregory-Newton interpolation formula then, we can express the sequence in terms of the Harriot sequences of binomial coefficients as 2 times h0 minus 2 times h1 plus 6h2 plus 6h3. and 0, h4. Okay, so that's up to degree 4 terms. That'll be an expression, a polynomial of degree 4, which is actually of degree 3 because this last coefficient happens to be 0, that will pass through those 5 data points. And what is it explicitly? Well, here are the h's. So 2 times 1 minus 2 times n plus 6 times here's n choose 2 plus 6 times n choose 3. Okay, you do a little bit of simplification, expand this out, collect terms, and you get 2 minus 3n plus n cubed. That's essentially the same thing that we got, what I said that we would get, if we did the linear algebraic approach. So this is a polynomial that goes through these data points when n is 0, 1, 2, 3, and 4. And we obtain it in a relatively simple way, just by doing this difference table, which is very quick, writing down the corresponding expression in terms of linear combinations of the Harriot sequences. And then we just have to remember what the Harriot sequences are, that h2 is just n choose 2, h3 is just n choose 3. Okay, and then we do a little bit of algebra, simplify, and boom, we get the polynomial that goes through the data points. So it's a beautiful method, very simple, very conceptual, and it allows us then to extrapolate and also to interpolate. And it's also robust. So let's have a look what would happen if we added more terms to the sequences. So suppose after we've done this, someone comes up and says, wait a minute, we found one more term, 78. That's our next term in the sequence. Now what's the polynomial that goes through those data points? Well, instead of having to do everything over again, we don't have to do everything over again. We just augment our difference table a little bit. Okay, so if there's a 78 here, then there will be, I suppose, a 24 here, 24 minus 34, and there will be a minus 10 here, and there will be minus 10, and then an 18 is minus 28 here. So then there will be a minus 34 there, and then minus 34 minus 0 will be a minus 34 up there. So the result will be that what we'll have to do is we'll have to take exactly what we've got and we'll have to add one more term. The term that we'll add will be minus 34, if I've done that calculation right, times the next one, which would be h sub 5, because it's 0h sub 4. So what we're doing is we would take this expression and then just add the new increment, add some new 5th degree term, which is another polynomial, onto what we've already got. So that's a very robust kind of situation. We don't have to do too much work. We don't have to do the whole thing over again. So I want to return to our geometrical thing just to finish and actually draw the result of what we've computed using the Gregory and Newton interpolation formula. So we've computed that the polynomial that goes through those 5 points is y equals 2 minus 3x is a polynomial on x plus x cubed. Okay, that's the polynomial. So we can graph that. Okay, it'll be, it's a cubic. Okay, excuse me here, we can go through there. Come down here, it's a cubic. And it turns out that if you graph it, it actually goes through minus 2 at 0. It goes something like that. So the best polynomial, the best fit to this 5 points of degree 4 or less is this curve here. It's actually a cubic, which is a little bit special because I chose those points not randomly. I chose them especially. And we see that it's maybe not so easy to predict that would otherwise do this. But this is what it does. And you can see the power of this, right? If you're an astronomer and you have some finite amount of data and you want to know where is the moon going to be, between 12, and 12 noon and 12 midnight, because we know there's an eclipse happening sometime that afternoon. You've only got data every 12 hours or 24 hours. You want to interpolate. You want to be able to figure out where the moon is at 3:15 or whatever the eclipse is supposed to be. So being able to make polynomial approximations to data points is very powerful practically. But we'll see that it also opens up lots of new theoretical possibilities for us too. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.